Hello everyone! Welcome to the presentation of our paper, Navigate Beyond Shortcuts, Debiased Learning Through the Lens of Neural Collapse. This work has been accepted by CVPR 2024 as a highlight paper, and the research was conducted by Witsardei Group of Fudan University. Our work focuses on the task of Debiased learning, where deep neural networks are trained on biased datasets, with each class dominated by some bias attributes like background and texture. The majority samples of each class are aligned with the bias attributes, where the minority of samples are conflicting with them. For example, in the figure below, the dogs and cats dataset has the bias attribute of color, where the class of cat is dominated by samples of black cats, and the class of dog is dominated by samples of white dogs. It's been discovered that models trained on biased datasets are prone to learn the shortcut correlation between ground truth labels and bias attributes, which induces low generalizability on out-of-distribution test samples. Therefore, the researches of Debiased learning focuses on mitigating the model's reliance on shortcut correlations. Existing works could be divided into three categories, which are reweight-based, augmentation-based, and disentangle-based methods. But they are all limited by extra and heavy training expenses. To tackle the problem, our research aims to achieve efficient Debiased learning without additional training expenses. As the theoretical background, our work is based on the neural collapse phenomenon. It has been discovered that, at the terminal phase of model training on unbiased datasets, the last layer feature space will converge to an elegant and symmetry geometry called simplex ETF. The geometry ensures the maximized class-wise separation of feature space, which implies the optimal generalization, robustness, and interpretability of models. In light of previous researches, our work extends the investigation of neural collapse phenomenon to biased datasets and analyzes the fundamental issues of biased classification. We trace the test set accuracy and neural collapse metrics on synthetic biased datasets. We observe the model training on biased datasets could be divided into two stages. In the first stage of shortcut learning, it first learns the shortcut correlations between class labels and bias attributes, and establishes a biased feature space converging towards the ETF structure. However, in the next stage of intrinsic learning, the models could not fully collapse into the ETF structure, since the biased feature space is hard to reverse. It results in a non-collapsed and suboptimal feature space, which limits the generalization capability of trained models. Based on the observation, we propose our avoid shortcut learning framework named ETF Debiased. We follow the idea of prime learning and use the ETF structure to directly approximate the perfect shortcut features in the first stage of training. With the guide of prime features, we encourage the models to skip the active learning of shortcuts and directly pursue the intrinsic correlations. In details, in the prime construction stage, we first construct the primes with a randomly initialized ETF structure. Each vertex of the prime ETF corresponds to a bias attribute. Then in the prime training stage, the prime features are retrieved based on the bias attribute of the input samples, to guide the optimization of learnable features towards the intrinsic correlations. We adopt both the classification objective and a prime reinforcement regularization loss to enhance the performance of Debiased learning. During the inference stage, we set the prime features as null vectors to perform unbiased classification with only the intrinsic correlations. To take a step further, we provide the theoretical justification of our framework. Following the analysis of neural collapse from the perspective of gradients, we analyze the pulling and forcing part of gradients with respect to both classifier weights and features. We prove that the mechanism of our proposed method implicitly plays the role of reweighting gradients, which guides the models to focus more on the bias-conflicting samples and mitigate the learning of shortcuts. To verify the performance of our framework, we conduct experiments on 2 synthetic and 3 real-world bias datasets. We choose 6 Debiased baselines, which covers the 3 categories of existing solutions. In the experimental results of Debiased performance, our framework consistently outperforms baselines in the generalization capability on almost all levels of bias ratio. It also achieves up to 6.6% accuracy improvements on real-world bias datasets, demonstrating its potential in realistic applications. In the visualization comparison of our framework, it's also notable that our method circumvents the wrong attention area in classification and encourages the focus on more discriminative and finer-grained regions. In conclusion, our work presents the theoretical investigation of biased classification and proposes an avoid shortcut learning framework named Debiased. For the first time, we investigate the neural collapse phenomenon on biased datasets and analyze the fundamental issues of biased classification. Our proposed Debiased achieves state-of-the-art Debiased performance with almost no additional training expenses. Our theoretical and experimental results both support the effectiveness of our framework. This is the end of our presentation. If you have any questions, please contact Witzerdai Group. Thank you for your listening.